Okay, let's wait for Zoom to connect. Okay. All right. So first and lesson will be out today, and at 6 p.m. it will be both on the class webpage and on EdSTEM. If you go to the lessons tab, there'll be a section for homeworks, and you'll find it there as well. And it's due at 10 p.m. Next Monday on Gradescope. Okay. Yeah. It's not on. Oh, thank you. It's on, but it ran out of battery. Okay, so you have to submit it on Gradescope. Okay. And so last class we talked about composing representations. We said we'll do this once, and we're done with it. We basically now know that the world is binary. We can basically represent everything, images, matrices, graphs, anything that you want, as 0, 1 star strings. And then we talked about what it means to be, what is the goal of computing. We're trying to solve some problems so that function. And for us, computing functions was basically from the domain of binary strings to the range of binary strings. Okay. We're just trying to, we have some mapping that's described to us, that is specified to us. We want to implement it or compute model, whatever. We're just trying to, we have some mapping that's described to us, that is a piece of basic operations performed repeatedly. Okay, and this led us to the concept of basic operations and to the most basic operations that we know of, which are and, or, and not gates. Okay. So what we're going to do today is to use these basic operations to define a formal model of computing, which is that of Boolean circuits. And then we'll talk about some very important concepts throughout computer science, that of equivalence of models, and kind of trying to show what you cannot compute. Okay. Let's see. I wonder why this keeps happening. Okay, so let's define Boolean circuits now. And I defined something else along those lines yesterday, which is an important concept for us, which is directed acyclic graphs. Which are also known as DAGs for short. Okay, so this is basically a directed graph with no cycles. All right, so you can take any directed graph, something like this. Okay, this is the DAG. There is no cycle within this graph, meaning you can't follow the chained arrows to come back to the same point again. Okay, so to define a Boolean circuit, you need a directed graph. Every Boolean circuit is associated with a Isn't the screen being shared? Hold on. Okay, so we need a directed acyclic graph. And once we have a DAG, we can define the model of Boolean circuits. So the definition is going to be a mouthful, but it has many ingredients, which I think I'm just spelling them out. It's a very simple model of computation. Okay. So that's why the big scary box. So we're going to parameterize or specify Boolean circuits with 3 parameters, for easy reference. So one is the number of variables, number of input variables. M will be the number of output variables. And S, which we'll call the size. N, M, S Boolean circuit is a DAG with the following properties. Okay, so the graph has exactly N plus S vertices. Okay, there are various conventions we can use. It's not that one is better than the other. We're just going to stick to the one that's in the textbook for easy reference and consistency. So we'll say, the circuit has exactly is a DAG with N plus S vertices, right? Out of this N plus S vertices, we'll designate N of them as corresponding to the input variables. Okay. So exactly N of these vertices are labeled as inputs. Which will denote xc all the way up to xn. Okay. So we're trying to do something which takes n bits as input and outputs m bits as output. All right. The other S vertices are what are called gates, meaning, each one is and or slash not. An AND operation or an OR operation or a NOT operation. Okay. And each AND gate has exactly 2 incoming edges. Variables and then output something else. OR gate has 2 in edges. Each NOT gate has 1 in edge. Okay. So that's, those are kind of putting some restrictions on what the graph should look like. Finally, we also say that M of the gates are labeled as outputs, which will denote y0, y1, y2, up to ym minus 1. Okay, I've just defined it syntactically. I haven't explained, how we use it or how are we going to actually do the computation. But right now, just think of it syntactically. You have a DAG, just hold on. You have a DAG, they have and, or, not gates, and then you have input variables. Some of these gates are also labeled as outputs. And depending on what kind of gate you have, there's some restriction on how many in edges you can have. Okay, yeah. You can, again, there are various conventions, you can just have a wire and say, put an extra gate or something like that. It doesn't kind of change, but you can just think that you can also label it as output. Okay. Any other questions? Words or looking like this, right? Okay. Again, I'm drawing it in a specific way. You should think of and then there is some connections, right? You should think of them as wires, like you really think of it as kind of an electric circuit. You have these wires which take the values across from one node to the other. If you have an AND gate, then you should have two wires coming in. Maybe this AND gate is going to a NOT gate. Okay. And maybe this is then going to an OR gate. My OR is starting to look like an AND. It should be a beautiful arrow. Okay, something like this. Right? Maybe this is the wire that is connected. Okay. And each gate might have many outgoing edges. It doesn't mean that, each one has exactly one thing. You could have a split here. There are various ways to draw a split. If that is actually allowed, that's fine. The only restrictions we're putting on the edges is on the incoming edges. Okay. And you will label something, maybe this is y1, maybe you have another AND gate here with something like this, and we call this y2. Okay. Any questions? Should really think of it as a physical circuit where you put on wires to connect the values. Okay. So that's kind of the syntactic definition. But how would you, define computation from it? So what does the circuit compute? Okay, so pictorially, just as a guess, intuitively what should happen if I ask you to tell you what is this computing, what would you do? Yeah. It should. So maybe let's say this is y0. Thanks for pointing that out. Okay. Yeah, we should have all indices starting from 0 throughout the course. Okay. So if I told you this and I ask you, okay, what is this computing, or how would you do the computation using this diagram? What would you say? Nothing formal, just kind of what's the intuitive thing that you think of? Any guesses? Yeah. Yeah, so basically you can kind of go from left to right, right? You just go and I tell you what are the values for these inputs, and then let's say these wires carry those values out. What does the AND do? And sends the AND out on the wire. Okay, does it make sense? You take, AND gate will take the values of the bits coming in on the input wires and send the AND of those bits on the output. Okay, you just kind of propagate this from left to right. right? But the left to right thing is very specific to how I'm drawing it here. But the way we defined it, there is no left to right. I just said you have a DAG, nothing else. Okay. So we have to, that's a good and bad. We have a nice mathematically clean definition. You just have a DAG. There's no notion of how you're drawing it or anything like that. But to define computation, we need some order in which you're going to do it, right? To go from left to right. How do I define that? Any suggestions? Yeah. Exactly, right? Any DAG, directed acyclic graph, has an implicit order in it. Okay, you can order the vertices in a very specific way, which is traditionally called topological sort in algorithms and discrete math. Okay, once again, we'll see an example through picture of what it is. Okay, so we say if G equals V comma E is a DAG for any directed acyclic graph, there is a way to label the vertices, which we'll call a layering or height function from the vertices to natural numbers, such that the edges are always go from something with a lower label to something with a higher label. Okay, it's a way to number the things so that they just kind of respect the ordering that you put on the vertices. Hold on. Okay, so such that for every edge I comma j, h of I is less than h of j. Okay, so for instance, if I gave you this DAG, right? So this is A, B, C. Maybe I have a D here. Okay, I have 5 vertices here, and you can check that this is actually a DAG. And the claim is you can put labels on these vertices so as to satisfy this layering property. How would I do that? What should be 0? I think I'll go with this being 0, this being 1, maybe this being, this could also be 0. This is 1, and oh no, this should be 2. This is 3. Okay, so I'm just doing it by just staring at it and guessing, but you can also do it in a more principled way. So what does this mean? So suppose I put all the vertices which are labeled 0 first. Okay, and then the one with label 1, the one with label 2, finally the one with label 3. Okay, now let me just redraw the same edges, C to B, C to A. Okay, D to B, D to E. A to B, right? And B to E. Okay. So under this layering, what it allowed us to do is kind of make sure that all the edges are essentially going from left to right. Okay. Again, there are many different numberings which give you kind of the same picture. The core is that the edges are going from left to right. That's what we really need.
So it doesn't matter that
Any other questions?
it doesn't matter that they're skipping a number as long as the number is greater than the
Okay. So once we have this, we can go from the definition of circuits to actual computation. Right? Again, if you have to write it formally, it takes a lot of words, but intuitively, you take the values from the left, which will be the inputs, and then kind of propagate it one layer at a time. Okay? Yeah.
How would you work? Because I know you said earlier the and OR gates have that input.
Mm-hmm.
What type of gate would be?
Oh, this is just to illustrate topological sorting.
Okay.
Yeah, this is not like connected to DAX per se.
Okay.
Because it has 3 incoming edges.
Yeah.
But this is just to illustrate topological sorting.
Okay.
Okay. Okay, so how do you do the computation? You say, given a Boolean circuit, a Boolean circuit for us from now on is just a DAG. We know with those properties, the edges are labeled something, there are some restrictions on the edges. Some gates are labeled with ands and ors and nots. There are input variables, there are output variables, that whole thing. And let's say I have n inputs, m outputs, and s gates. How do you do the computation? What we just said. Again, I'm going to write it down in a little bit of gory detail, but intuitively, what you do is put the variables first and then propagate the computation, right? So we say layer the DAG by a topological sort. So that all input vertices are in layer 0. That's by convention. I just want to put them all in layer 0 to make things consistent and easy. Okay. And then we kind of do it one layer at a time. Suppose we have computed, meaning we've assigned kind of 0 or 1 values to what each node is supposedly computing in layers 0, 1, all the way up to maybe some k minus 1. Okay. Now, for each vertex in layer k, you compute whatever the gate is telling you to do, right? So if an AND gate, assign it the value of AND of its incoming wires. Okay. And if an OR gate assign it the value of OR of its incoming wires. not, not, okay. And the output at the end is y value, which is 0, 1 through the m, which is just, you think of putting y0, y1 up to ym minus 1 together. Right, so we had some special nodes marked as outputs, just put them, print them out in that order. Okay. Any questions? Okay, so now we have a fully specified model of computation. And at the end of the day, given any circuit, we have a function that this circuit computes. Right? So it takes n input values and outputs m output values. Okay. And finally, so this is an important distinction to make, which is between specification and implementation. We'll see this again and again throughout this course, which is following. We say a circuit C computes a function f if f of x equals c of x for all x, all valid inputs. Suppose I have a function on n input strings. That's my specification. I ask you to compute this function. You go and design a circuit. We say the circuit computes a function if this, if c of x is exactly what f of x should be for every input. And there may be many, many different circuits which compute a specified function. All right. So this kind of distinction is often, it's not kind of gets hidden, but it's good to keep that in mind. Okay. Any questions about this? About the model? Okay. So as an example, I think we had the and the circuit for XOR, right? We can say X0, X1. Class, but I'm redrawing it. Okay, so this is and we had an OR. Okay, so this is a circuit for computing the XOR function on 2 inputs. So the output would be this guy. Okay. Any questions? Yeah. Yeah, the f is a function which takes a string of n bits as input. That's it. Circuits, that's, kind of, you're hinting at an important point, which is circuits by definition are only useful when you fix the number of input bits. Okay. So you kind of really imagine taking a circuit board and soldering on the wires, and the only thing you get to change is what inputs you plug in. Okay. There's nothing else you can change. You cannot kind of increase the size of the circuit or anything, because then it's a different circuit. In the model, as we defined it, the number of inputs, the number of outputs, and the circuit, everything is fixed. Okay. Any questions? Any other questions? Yeah. We could label results of the gates as well. Sometimes it's more efficient to kind of, maybe reuse this. That could also be, a good thing to do in some scenarios. Is the internet flaky just for me, or is it the same for everybody in this? Okay, that's good to know at least. I don't know why, but it makes me feel better. Okay. Is it again just this room, or do you see it in other classes as well?
Literally every.
Okay.
Something specific to the M1 now.
I see. Okay. Nope, it's not okay yet. Okay. So, we can reuse the output wires, and actually there's some really interesting questions, to play with here. Sometimes if you're taking any architecture course, VLSI design and so on, you can be very clever about how to use the circuits. You can really think of, putting down the wires costs you something, each gate costs you something. How can I find efficient implementations and all of those things? Very interesting questions. We're not going to touch any of them. Okay. But it's good to know that, there's a very simple model, which is, we've described it, and we'll see what it can and cannot do in a little bit. Okay. But, if you look at this entire thing, one question should be bugging you a lot. Okay. I won't entertain any other question until you identify my question, which is, what should be the question that's bugging you? So there's something arbitrary in the way I define the circuits, the model of computation. Yeah. It's okay. Okay, I'll tell you what should be bugging you, which is, there's something ad hoc in the choice of and, or, and not. Why those three operations and not something else? Why don't I add something else into my mix? What is so useful about just these three operations? Or why do I even have to keep all three? Maybe I'll drop something. Yeah. Yes, exactly. So kind of lead up to it. And I mean, there's some redundancy even within and or not. But to lead up to it, let's look at some other operation, which actually kind of makes everything cleaner, at least in terms of definitions. Okay. And that's the NAND operation. But first, let me ask the question. Why the choice of and or not? What happens if I drop the and just give you or and not pieces? What if I drop not and I just give you and or pieces? Can you still do some stuff? Okay. But there's one operation which is actually much more useful, and that's called much more useful in the sense of actually being more succinct. It doesn't kind of make any other difference, but make things a little cleaner. So the NAND operation is just like and or not. It's a basic operation in the sense that it takes 2 bits as input and outputs a single bit. And what does it do? It's NAND of A comma B is defined as not of the AND of A comma B. Okay. So NAND is not AND. Okay. All right. And the way it's usually denoted is the following. Again, it has 2 incoming wires, right? You have the usual, you draw the usual AND gate, but then you put a circle in front to signify that you're doing a NOT at the end. Okay. So this is the pictorial representation of NAND. All right. And once we have NAND, we can also define NAND circuits. Okay, so N, M, comma, S. It's really the same definition. Everything is the same. And it's a NAND circuit is a DAG. But now the only difference will be that the gates, the only allowed gates are the NAND gates. You don't have AND or NOT, you just have NAND gates which are allowed. Okay. So you once again have N vertices labeled inputs, x0 all the way up to xn minus 1. The other S vertices are labeled NAND, and each has exactly 2 integers. Okay. And finally, we have M vertices, which are also labeled as outputs. Okay. And given a circuit, we can also define computation, which is do a topological sorting, go from left to right to compute the values, right? So given an NAND circuit, C, we can define let's see. Okay, so just as we defined it for Boolean circuit, we can also define a corresponding function that is computed by the circuit. Okay. Now you can ask, I had 2 different models, right? At least on, on paper right now. I have one thing which is, just using NANDs, one which is using AND or NOTs. You might ask, which is more useful? Are somehow kind of each of equal power, or is one better than the other? How can we reason about what they can individually do? Okay. So we'll get to that in a bit, but let me first show you some couple of illustrations of why circuits are kind of a very natural model to begin with. There's something that I said in the last lecture, which is that circuits are one of the first devices which are implemented are as physical things. Okay. And there's some really cool demos you can find on it. For instance, let's see. Where does this go? Okay, so you can see this is computing R. Computing in the sense that the water will go to the next sort of pipe, only if the corresponding bits are doing exactly what they're supposed to be doing. Right? So this is R, only when there's water flowing through either one, you get through. XOR, you can see, is really clever. And of course, both have to come in. Okay, this is just kind of, one sort of toy demo, but people actually use something much more sophisticated than this, kind of based on the same principle in some fields. Okay, there's another. Okay. So there's something called the digicomp, which is, I think, really is kind of a programmable circuit. So it's kind of a toy back in, I drop the balls, depending on the configuration, you compute something. Okay, and kids who are 5 years old will get a puzzle saying, okay, design a circuit for computing the majority of 10 bits. I'm kidding, of course, but not kids, who are 5 years old, but something like this. Okay, so you can configure these knobs, kind of tell you how the balls are supposed to go. And there are some large scale physical kind of, things to play with. If you've been to the CS building at MIT, they have one in their lobby. Okay, you configure these real wires, not wires, but kind of the levers which tell you where the ball should go. That's what you play with. And then you drop them. Okay, besides this kind of toys to play with, I'd say, most of modern computing actually is built on top of circuits, As a basic model, they're very important because you can implement them on physical devices, right? So we're starting with that. That's the motivation for first studying circuits for two reasons. One, they're really, what gets used in practice, and they're a very easy model to kind of
Professor? Yeah. So for this, did you say size? Size, okay.
S is like the number of gates.
Okay, thank you.
Sure. Okay. Okay, so we have, decided, okay, we're going to define model of computation, but we already have two models of computation. One is the Boolean circuits, one is the NAND circuits, right? We had to kind of, pick a lane, right? Which is pick one model. Do we have to? So let's think about that. So if you want to compare the two models, let's see if you can actually, argue one is more powerful than the other. Now, suppose I have a NAND circuit. Can you compute it? NAND circuit, can you simulate it using a Boolean circuit? Meaning, is there a Boolean circuit that would also compute the same function? Any guesses? Yeah?
Intuitively, yes, because like, I mean, I just like anecdotally heard that both like model computation could compute like any
Right, but that's true. But I think we'll get there a little bit later. Right now, the comparison is a little bit even easier than actually showing that they can do much more grander things. Okay? Yeah.
Can you just break down every NAND gate into a standard NOT gate?
Yeah. So one kind of reason these basic operations are so easy and good for modeling is because to show kind of translation, like, saying that one model is as good as the other, you just have to show how you can implement these basic operations. Okay. Once I do that, you can do everything else that you're using these basic operations to do. Okay. Think of as Lego blocks. Now, someone told you, okay, here's a different way to build the same block. Here's a different way to do the AND gate. Then wherever you're using AND, I can go and replace it with this block, right? The same with NAND. Okay. So a NAND gate can easily be simulated by Boolean gates. How? It's kind of, maybe in the name itself, right? This is the NAND. Every time I see a NAND piece, I'm just going to go ahead and break it up into an actual AND gate followed by a NOT gate. Okay. So imagine, someone gave you a NAND circuit diagram. I go and replace each NAND gate that you have with these two things. Okay. That box is now this box. The end computation is not going to change because the output, this wire will carry the same value as this wire. I'll keep everything else, all the other connections the same. Okay. That's one thing. And now let's think of the other comparison. At least in this view, it seems like NAND is no more powerful than Boolean circuits because I can just replace each NAND. How about the other way? Can I compute, let's say, maybe let's start with something more basic. Can I compute NOT with just NAND gates? Yeah. Yeah, excellent. So if I take NAND of A comma A, what will it give me? It'll give me not of A. Okay, so just let me show that as a diagram. So suppose, I have a bit A, which is going to a NOT gate, right? So I want to say this is equivalent to doing the following. I'm going to splice or kind of split this wire into kind of two wires. So the same values being propagated onto these two wires. And then I'm going to pass it through a NAND gate. Okay. And you can check, so if A equals 0, what is NAND of A comma A? It's a not of 0 comma 0, not of the AND of 0 comma 0, which is 1, which is what it should be doing. If A equals 1, it's not of the AND of 1 comma 1, which is going to be 0. Okay, so we can at least simulate not with a single NAND gate. Right, so every time you see a not, you just kind of splice the wire and then you put a NAND gate there. How about can I compute AND with NAND? Can I do something similar if I had to compute the AND of 2 bits? Any suggestions? Yeah.
Yeah, you just do that, and you just did above the non-gate, and it's the NAND as a
Excellent. So basically we just saw how to compute not, right? But how is AND? We know that not NAND is not of AND. So if I take a not again, what do you get? AND. So AND is just a not of NAND. Okay, it's just a double negative. You kind of gets canceled, get back AND, right? But we know how to compute not. So I would just do NAND of A comma B, and then NAND of A comma B. Okay, so if I had A and B, then the circuit would look something like this. Right, I pass it through NAND once, sorry, then split the wire again, pass it through another NAND gate. Okay, so 2 NANDs will give me an AND gate. All right, so this is equivalent to just doing the AND. Okay, so we're only talking about the basic operations, kind of using one operation to simulate the others. Okay. And finally, let's do OR. How can I do OR with NAND? Any suggestions? It's a little bit more kind of, hairy to do it. You just need a couple of other operations, but basically you can still do it. So OR of A comma B, you can write it as NAND. So when is OR false? Right, when both A and B are 0, right? Which is when both not of A and not of B are 1. So you can use that reasoning to come up with this formula. So OR is exactly NAND of not of A comma not of B. So if both are 0, then the inputs to NAND would be 1. So you get back 0. And if either one is Okay, let me just try and record from the iPad now. Confirm. Can you hear me on Zoom? Okay, good. All right, let's see if this works. Unfortunately, I can't see the chat messages now, but just you can unmute yourself and ask them if you want to, if you have any questions. Okay, so we can do OR with NAND operations as well. You know, pictorially, it looks something like you have the OR gate. Whenever you see it, you would replace it with something that has 3 NAND gates. Okay, so we know that we can simulate NAND with just Boolean gates, and vice versa is also true. We can go from AND or not to just NAND gates. Okay, so we can simulate OR with 3 NAND gates. Okay, so what does this mean? In terms of what they can compute, the 2 models that we defined are actually equivalent to each. Okay, so there are some differences in efficiency perhaps, but whether or not they can compute something is exactly the same. So this leads us to the following theorem. Boolean circuits are equivalent to NAND circuits in computational power. Okay, so equivalent meaning if f is a function that is computable by a Boolean circuit, meaning, you know, I have a function on n bits, and I ask you, okay, is there a Boolean circuit that can compute this function? The answer to this is true if and only if there is also a NAND circuit computing the same function. Okay.
Professor, what is the specific definition of computational power here? Because I think, colloquially, it's, you know, oh, I have a powerful computer means it's faster, or, you know, it's better somehow. What does computational power mean in this context?
Right, so that's a good question. So the question was, you know, right now we're just saying whether something can compute the function or not. But what would it mean to say, okay, this computer is faster than the other? Okay, that's something, you know, that we can get to later in the course, and just as a remark. But right now, we're mainly interested in answering kind of the first question, which is, can this model compute the function or not? Okay, once you know that, then you can ask, you know, our Boolean circuits, some are faster than NAND circuits. They're not really that kind of they're both very comparable in how much time or how much resources you might take. But you can already see that there is some slack, right? If I had a Boolean circuit, when I write it as a NAND circuit, I have to increase the size a little bit. Right? If I have an OR, then I need 3 NAND gates to it, right? In terms of hardware, you're kind of using more resources a little bit at least, okay? And the same vice versa. If I have a NAND to implement it using Boolean gates, I need 2 operations. Whereas with a NAND operation, I can only do 1, okay? And there's a good reason we kind of talk about it at this high level right now, because there are different, you can imagine, one hardware manufacturer is really manufacturing NAND gates. One is manufacturing Boolean gates, okay? So, at the end of the day, they're both doing very similar models and the cost is also similar. So you're going to focus on whether or not you can compute something first. And then, you can kind of reason about things later on. And we'll do that in the next lecture as well. Okay. All right. So, okay. So we have these 2 models of computation. We know they're both equal. So, we're just arguing, kind of putting them against one another and saying that both are the same. But how powerful are they as a whole? What can they actually compute? And what can they, are there any limitations to what they can do? So this leads us to kind of our next question. But before that, let me summarize. It's a good checkpoint to have. So summary. We define the model of Boolean circuits. We define the model of NAND circuits. And we looked at the concept of equivalence of computational models. Okay. This notion of equivalence is something that's going to come up again and again throughout the course. So just keep that in mind. This is kind of a very nice illustration of equivalence because you can really see what's happening here. Okay. But it's a good model, but are they really useful? Are these useful for computing? Actually, let me check that it's being recorded still. Okay, it is. Good. Meaning, okay, what if I had to compute the majority function on 10,000 bits? Can you write me a circuit for it? Can you write me a circuit for it? What if you had something more complicated? I had to multiply 2 10,000 bit numbers. Is there a circuit for it? Anything like that. Are there functions which cannot be computed by circuits? Is there a function on n bits for which there is no equivalent circuit which can compute it? Okay. As it happens, we are somewhat lucky in that this simple model of computation is actually universal as long as we fix the number of bits. Okay. So this leads us to one of our first kind of, complicated theorems to prove. This is going to be a little bit more involved than what we did, but it's also very important. So what it says is that every function, no matter what function you have, there is actually a Boolean circuit which will compute it. For every function, can be computed. By a Boolean circuit. You can also specify a size, which is a constant times n times m times 2 to the n. Okay. Every function can be computed by a Boolean circuit of at most this much size. is exponential in the number of input variables, but there's still a circuit which can compute that function. Okay. And this would not be true, as you'll see in the homework, if you drop, let's say, the NOT gate. Okay. So having all three is critical here. Okay, at least two of them, which is not or and, is critical. Okay. Any questions about the statement? All right. So let's kind of make our way towards proving this theorem. We'll prove it in two modular steps. And here in this class, I'm going to prove it for m equals 1 only. So let's consider a function which has exactly one output bit. All right. So the general case is, very similar. So I'll leave it for you to think about. And if you have any questions, the TS will cover it in the discussion section. But focus on the most important kind of non-trivial step, which is, let's say, a function which takes n bits and outputs a single bit. Now, maybe it's checking whether the sum of the bits in your string is even or odd. Okay, that's a function. Is there a circuit which computes that function? So we have a function which is specified for us by a truth table. You can think of it as being, you write down the entire truth table. So we have all input strings here. Maybe something like 0, 0, 0, 0, 0, 1, and so on. And then you have the output values. Maybe this is 0 here, 1 here, 0, 1, 1, so on. Okay. How many rows would I have in this table if I had to write down the entire function? Any guesses? 2 to the n, right? Because I need to write down one row for each possible input assignment. So I have n input variables, each corresponding to n binary values. So there are 2 to the n rows. And for each one, there is an associated 0 or 1 as specified by the function. Okay. If it helps, you can think of as a function being like, maybe is the measured of the number of bits 0 or 1. Is the sum, 0 or 1 mod 2. Okay. You can think of something specific like that as well. Now, what's our task? No matter what the function is, we have to argue that there is a circuit which can compute it. How do we do that? So it kind of seems somewhat messy, right? How would you even come up with a single circuit which captures all of these things? Yeah.
So equal all the rows with 1
Okay.
for each 0 bits.
I think I know where you're going. So let me highlight that. So the idea is something that we did when we came up with the specific circuits in last lecture. For XOR on 2 bits, I wrote down some circuit, and that was based on some intuition, which is for any function like this, let's look at the strings which actually make the function evaluate to 1. Okay. So in all of these rows, let me pick out those rows where I'm taking the value 1. Okay. And let me look at all those input strings. So essentially, my function is 1 if and only if my input string x is part of the set S and is 0 otherwise. It's kind of a different way of interpreting the same function. Look at all the rows corresponding to the value 1. My input string is, whatever is some other string. If it is one of these rows, then you should output 1. Otherwise, I'm going to output 0. Okay. So to do that, I'm going to split it up into 2 tasks. Okay. So for each string, we are always going to use modularity. In some sense, we're going to build pieces and put the pieces together to build more complicated objects. Okay, so here I'm going to define a new piece that we're going to first build and use this to get a circuit for general functions. So what is the piece? I'm going to define a new function for any string alpha. There is an associated function which I'll call E alpha, which takes n bits as usual as input and just checks, it's kind of equality. It checks if my input is alpha and 0 otherwise. Okay. Kind of, it's just checking if my input string X equals a specific string alpha, and otherwise it outputs 0. There's only one input where it will be 1 and is 0 everywhere else. Okay, so this is one special function. So as an example, let's say alpha is the string of all ones. What does the function corresponding to E alpha, what function does E alpha correspond to in this case? Any guesses? Yeah. Exactly, right? This function, when alpha is all ones, evaluates to 1 only if all of the input bits are 1. You cannot have a single 0, because if you have a single 0, then you're not identically equal to the all one string. Okay, so this is just AND of all the input bits. And as suggested, we can compute it as a Boolean circuit by chaining ANDs. Ooh, let me not do that. Okay, so I have to compute AND of n bits. So, but in our definition, in our basic operation, each AND gate can only take 2 bits at a time, right? I can't just say, okay, go and compute AND of 10,000 bits. That's not a tool that I have. What I have are the basic operations, which only take 2 bits at a time. But it's not a big issue because I can chain them one after the other, right? Computing AND on 10 bits is like computing the AND of 2, then AND of that with the 3rd bit, AND of that with the 4th bit, with the 5th bit, and so on. So that's exactly what I'm going to do. Right, I have multiple AND gates here. Kind of one chains into the other. Oops, hold on. Okay, any questions about this? So this is one circuit for computing the E function for the all one string. Okay, so it's E for equality, really. You're just checking whether the input string equals the specific string alpha you have in mind. All right, any questions about it? So this is my circuit for computing the E all one string. How many gates am I using here? Just to kind of checks, just to kind of have a count. The number of gates used is n minus 1, right? So I need n minus 1 AND gates, so that's the size. All right, remember for size, we only count the number of gates used, not the number of input variables or the wires. It's just the number of gates that we use. Okay. All right, so it seems like, at least we can do the E alpha for, one specific alpha. But what if, I have to compute another function, right? So let's look at some other example. As I said, we are going to build pieces and put them all together in one go in a little bit, right? So here's one specific function which we saw how to compute using a Boolean circuit. But what if, maybe I had my alpha was all ones, except the last bit was 0. How can I compute the equality function corresponding to this alpha using a Boolean circuit? Any suggestions? Yeah, not the last bit, right? Because we already know how to do it when everything is all ones. And now we just have to kind of do the same thing, except for the last bit, right? Wait, I'm not the host.
I'm the host. I'll make you the host.
Thank you.
There you go.
All right, thank you.
Just so you know, your iPad was at 5%, so you might want to charge it.
Yeah, it is charging now.
Oh.
It was at 70% when I started.
Yeah, batteries, man.
All right, okay, so we're back. So we have all ones and a 0 at the end. So the only thing that we'll do is kind of copy this entire circuit, right? And okay, but we will put a NOT gate here. Okay, any questions about this? So we defined a new circuit now for computing this function, which is checking the equality of all ones except for the last bit being 0. Now we can hopefully identify the pattern, right? What if I gave you another string alpha, which has some zeros, some ones, whatever it is, right? Maybe how about any alpha which is a 0, 1 to the n string now. How can I compute the equality function using a Boolean circuit? Any suggestions? All right, okay. Yes. Exactly, right? So you just have to NOT all the wires which are coming out of variables which you have to check for 0, right? Checking whether something is a 0 is the same as checking whether NOT of that variable is a 1. So that's what we're going to do. So I'm going to copy this and say, okay, put it here. But now we'll have some, let me say, okay. I'll put it in gray color because it's not as if I'm drawing on everything. It's just to say that you put a NOT gate. Maybe let me do it this way. So on the input wire corresponding to x0, you put a NOT gate if alpha 0 is 0. Okay. And the same thing here. Put a NOT gate if alpha 1 is 0. Same thing. Put a NOT gate if alpha 2 is 0, and so on and so forth. Okay. Question for, right? And the answer will come in a second. And the answer is that we can use these as pieces by themselves without opening up the circuits to compute any function. Okay, so always as computer scientists, we like to do two things. Either we'll solve the problem by kind of indirection, we'll point to some other library, or we'll break it up into pieces, each of which we can somehow reuse. Okay, so that's what we are doing. Kind of we use the idea behind the same idea for designing all of these E alphas, and now we're going to put them together in some way, right? So what did we learn here? Summary. We can compute the E alpha functions for any alpha using Boolean circuits. Okay, how many gates would you need in the worst case? Maybe I'll have n NOT operations and n-1 AND gates. They're always there. So the size is always less than or equal to n plus n minus 1, which is 2n minus 1. It's kind of a small enough circuit. We are having at most 2n minus 1 gates, and we can compute any of these E alpha functions. Okay. All right. So now we come to why we are looking at these E alphas, which is plain and we can use E alphas to compute okay. I'm putting compute in quotes because we know that anything can be computed by Boolean circuit. It's not a tautology in the sense that we can compute it with relative ease given what we've already accomplished. Okay. So why is that? So suppose, let's go back to where we started out from. So we have a function f, which is specified to us by some truth table. Right? So we have inputs and we have output. I mean, you have all possible strings. And for each string, you have a 0 or 1 to designate the function's value. Okay. So what we're going to do is in this pick out all the rows corresponding to ones, right? So S is going to be alpha such that f of alpha is 1. Let's look at all of these strings. These are all some alphas. Let me just give them some numbers just to be very concrete. Maybe it has some capital N many alphas here. Okay. And to compute f, is equivalent to checking whether my input string x is one of these alphas, right? If it equals any one of these alpha 0, alpha 1, then I should output 1. Otherwise, I should output 0. So how can I accomplish that using the E functions that we already have, the equality functions? Any suggestions? So I want to say that I can write down f of x, any function, using these E alpha i's. Yeah.
Get all the alphas of the sub-alphas into a bunch of chain boards.
Yeah. So we have to check if x equals E alpha 0. If E alpha 0 is 1, we should output 1. If E alpha 1 is 1, we should output 1. If E alpha 2 is 1, we should output 1. So if any of this E alpha i's output 1, then we should output 1. Okay. So let me write it down here. Okay, so if x is equal to any one of alpha 0 up to alpha n minus 1, we should output 1, else we should output 0. Okay, so that's why we looked at the C functions, because they allow us to break up the whole task into the small pieces. All right, so again, we can't say, okay, take OR of all of these things. We had to do ORs 2 at a time, so we just kind of chain the different OR operations, right? So meaning what we're going to do is I'm going to kind of slightly in the interest of keeping things a little simpler to draw the input variables multiple times, but because otherwise it just becomes too difficult to see what's happening, I think. Okay. Okay, you can imagine I have 1, I have 2, I have 3. Oops. Okay, and many more like this, right? Okay. So this is meant to be E alpha 0. So there's like one output, which is E alpha 0 here, right? So there's one, which is E alpha 1. This is E alpha 2, and so on. Okay, so we're just putting all of these circuits one on top of the other. The input variables are all shared, but as I said, you should just imagine kind of sending these variables to every one of these copies. Okay, does the diagram make sense? I'm just copying the same E alpha I, this kind of same idea for designing each E alpha I, but then I have all of the different E alphas on one on top of the other. Okay, and these values are now going to go into an OR. Maybe I should draw it a little smaller. So this goes here and this here. Okay. So when we chain everything together, we get our Boolean circuit for F. Any questions about this? So this will be the output. Let's say, let's call it Y0. Okay. So, we're almost done. Let's just, so what did we really want to show, right? So we wanted to say that every function has a Boolean circuit. We kind of showed that already. Let's just, there's also a remark about the size. How many gates would the above circuit need? We know how many gates each E alpha I would need, right? So we can use that as a kind of good starting point. So each E alpha I need something from, up to 2n minus 1 gates. If I have capital N many E alpha i's, I get this much. Okay. But then I also need some extra OR gates, right? I need these extra OR gates to kind of daisy chain each of these E alpha i's, right? How many of those would I need? How many, roughly capital N minus 1. Okay, because I have capital N of this E alpha i's, every 2 I need a new OR gate. Okay, so this kind of almost answers the question, but how big can this capital N be? Remember, what was capital N? It was the number of input strings which could have made the function evaluate to 1. Right? So how big can this set, how big can this number be? Any guesses? Yeah? 2 of what? 2 times little n? No, it's much bigger, much bigger. Yeah? You raise a hand, right?
Yeah, well, the maximum possible is if all the possible strings ended up being 1.
Yeah, so it's 2 to the n. You are close.
Oh. Oh, that's
Okay, so the number of possible strings is 2 to the n, right? Presumably, every one of them makes our function evaluate to 1. I mean, it's kind of if that's the case, we're using this dumbest possible circuit, but it is a circuit which computes the function, right? We're just saying, okay, you had to output the constant function 1, but I'm just going to write down all the possible strings for which the function evaluates to 1, and it can be up to 2 to the capital N. Sorry, 2 to the little n. So we know that the number of possible strings that can make the function evaluate to 1 is at most the total number of strings, which is 2 to the little n. Okay, so we get something like 2 to the n times 2n minus 1 plus 2 to the n minus 1, which is really like 2 to the n 2 times. Okay. So, we don't care about the constants as much yet. So this is just of the order of n times 2 to the n. Okay. So in summary, what we showed is that every function has a circuit of this size. Okay, every function, as long as it has a single bit output, has a circuit of this size. All right. Any questions about this construction? Yeah.
To apply it to m is greater than 1, we just reapply the whole same trick, but for each of the outputs.
Exactly, right? So that's an excellent point. So let me note that down. So remark, we did it for the number of output bits being 1. Okay, but otherwise,
I'm guessing he gave up because he gave up last time when it was close to the end of class. So I'm just gonna wait till 150 and then bounce.
Oh well. I have to rewatch this one anyway. I was mostly distracted with trying to set up a Wi-Fi network.
I'm never doing remote again. I'm only doing it because I'm sick, and this was terrible.
I just woke up late.
Yeah, not worth being lazy.
It did work out though. I got to eat, and I think I'll have this thing done before I have to run off to my 2 o'clock class.
Yeah, I don't care that it's recorded. Technically, I'm in control of the recording, actually, because I'm the host now. So
Ooh,
I guess I could stop
interesting.
it if I wanted to.
Are we being recorded right now?
Absolutely.
Oh, we are.
Yes.
This is hilarious.
Yep.
This is
Hi.
hilarious. Hello, future students.
The lecture was amazing.
Yeah, exactly. Absolutely. 10 out of 10.
Really like the part where he introduced all of those
The bits.
conspiracy theories.
The bit, yeah.
Yeah, and the bits. Yeah.
Okay, well, it's 1:49:39, so I'm gonna call it. All right, everyone, enjoy your cloud recording. I'm gonna stop recording now. Bye.
I'm going to enjoy this thoroughly.